So this is Monolithic PLL. So as of now we discussed individual block diagrams. Individual block diagrams like so phase detector we discussed separately, low pass filter, amplifier, and finally VCO. Okay, so these are the individual ICs also available in the market. So all the parts are integrated in one place and they designed one PLL in a single chip. Okay, so here there are so many ICs are there. So for example, and here there are some SC by NE. So this is the company name, and 560 series. 560 series is nothing but 561, 561, 562, 563. So 564, 566, 567, like this. There are so many are there. Okay, and in even if you go for national semiconductors also. Okay, national semiconductors also it has LM560 series. Okay, out of all these series, so generally, so the most used thing is so 565 is there. So this is most used. So 565 series out of all these things. Okay, so this is a 565 series here. So this is SC NE 565. Okay, so this is the IC. And now coming to the internal block diagram of again so monolith is IC block diagram. So internal block diagram is again the phase shifter is there, phase detector is there, applied by the amplifier, then applied to the low pass filter. See, this is the resistor you are connecting here and the capacitor, and you're taking the dimmer. So across the capacitor you are taking the output. So this is the low pass filter. So you see this combination form a low pass filter. Okay, and if you see, observe that resistor value, this is 3.6 kilo ohm resistor, which is internal part of it. So resistor is 3.6 kilo ohm resistor, it is fixed. You cannot change it resistor value because this 3.6 kilo ohm resistors are designed internally. Okay, and phase detector applied by the amplifier and applied to the low pass filter or low pass. So actually what we discussed is, so a phase detector applied to the low pass and applied to the amplifier. So what happens is, when the output is generated by the phase detector, it will block the high frequencies, allow the low frequencies by the low pass filter, then it will amplify. But here what happens is, phase detector whenever it is giving the output signal, it will amplify, then it will eliminate the high frequencies. Both are same. Whatever the finally it comes to the VCO is, so after eliminating the high frequency component, you will get the only low frequency components. So here what we are doing, we are amplifying the first we are amplifying, then we are eliminating the high frequency. What we discussed in the basic block diagram is, first it is eliminating the high frequency components and amplifying the signal. Both are same, no issues. Okay, and this is the part we discussed as just now. So this is a voltage control oscillator. So RT CT what we discussed previously. So CT is the capacitor which generates a triangular signal like this. Okay, and you will observe one important point here. So here we are applying VCC and here we are applying minus VCC. In the voltage control oscillator, so what we get, so KV equal to 8F0 by VCC, we got it. Yes or no? So that is nothing but previously what we get it is 8F0 by VCC. So in this previous circuit diagram, so here we are using only one single VCC here, and but here so we are using two VCC. So for that reason, in the place of KV, I am rating the place of VCC KV equal to 8F0 by V, where V is nothing but VCC minus of minus VCC. In the place of VCC, we are replacing with V, where V is equal to VCC minus of minus VCC here. So this is the block diagram of it, and it's okay. And come here. So this is the first thing is, here in this topic we need to calculate two frequencies. That is, one is a lock-in range frequency, and second one is the capture range frequency. Okay, in the lock-in range frequency, so from what we discussed in the morning also, balanced modulator, we got the error voltage and control voltage. Error voltage is nothing but output of your phase detector. So that is V is equal to K pi into pi minus 5 by 2. Okay, so now once you got the error voltage here, so that is passing through the amplifier. So once it is amplifier, we see A is nothing but, so gain of it. So A is nothing but gain of the amplifier. So what it will do, it will take, this is the output output of the phase detector, and it is passing through the low pass filter. Yes or no? So this output of the phase detector, and the output of the phase detector is passing through the amplifier. So means, so this is the gain of the amplifier. So gain of the amplifier, output of the amplifier is nothing but VC input is this. So the output is equal to gain into your input signal. This is the control signal. Is it right? So see, coming back and see, so after this you are getting the VC voltage here. This is VC voltage, and here we are getting the error voltage here. Okay, so error voltage. So error voltage is nothing but this. So K pi into pi minus pi by 2. Okay, and so once the VE, you are getting VE, and it is passing through the amplifier. So what is the gain of amplifier? I am taking it as A. So output of the amplifier V becomes the gain times of your input signal. So that what I am getting. So VC is equal to A into K pi into pi minus pi by 2. Okay, and these two are we got from the balanced modulator. And now come back to the, so now VC, what is the VC? So control voltage, it makes to shift your VCO frequency, free running frequency, to the new frequency. So voltage control oscillator, it has some frequency. It may, so depends on the control voltage, it will decide that how much output frequency it has to be generated by the voltage control oscillator. So for that I am just taking the F is nothing but new frequency, and F naught is nothing but so center frequency or center frequency or free running frequency here. Center frequency or free running frequency. Okay, free running frequency here, and kV into VC. kV into VC is nothing but what is where kV is equal to F naught by VC only. Okay, delta of F naught. So means F is equal to F naught into delta F naught means. Now F is equal to what? F into, so the already free running frequency is there, plus some delta F naught. Delta F naught means the change that depends on the VC. In the place of delta F naught, we are keeping so kV into VC. Okay, so now when the PLL is locked, so F is equal to Fs, so that is the input frequency, and so that is equal to F naught plus kV into VC here. Okay, so you rearrange the equation, you will get VC is equal to Fs minus F naught by kV. Okay, when the PLL is locked entities, so that is output of the VCO, output frequency of VCO must be matched with the input frequency. So that is Fs equal to F naught. Okay, so from that VC equal to Fs minus F naught by kV here. Is that right? So from that VC is equal to what we got. So VC is equal to A times of K pi into pi minus pi by 2 equal to Fs minus F naught by kV. If you rearrange the phi value, you will get pi by 2 plus Fs minus F naught by A times of K pi into kV. So here the phase difference, this is the phase angle which gives the phase difference between, so phase difference between input signal and output signal of input frequency and output frequency of the VCO. So pi indicates the phase difference. Phase difference is nothing but what we call phase difference between input frequency, input signal to output of the VCO. So as we discussed in the balanced modulator, what we are, so in order to make Fs equal to F naught, so what we'll get, the phase angle must be 90 degrees. Yes or no? So what we discussed in the morning, in order to make it Fs equal to F naught, the phase difference between the input signal to output signal of VCO should be 90 degrees. If you substitute here pi by 2, so pi by 2 cancel, it makes 0. So Fs minus F naught by denominator is equal to 0. So if you send this denominator, the side becomes 0, so Fs equal to F naught. So it is satisfied, right? So in order to make Fs equal to F naught, the phase angle should be 90 degrees. So in between the two signals, right? So this explains, this pi explains that the phase difference between the two signals. Okay, now so coming to this again the next point. So the maximum voltage can be obtained from the phase detector. So maximum voltage means there are the three phase angles. Let us say, suppose if it is 0 degrees or pi by 2 or pi, what happens? Okay, so this is the maximum magnitude voltage. Magnitude voltage here. Magnitude is nothing but, it may be plus or minus, but we should get the maximum voltage. Okay, can be obtained from the phase detector when pi is equal to 0 or pi by 2. Why? Because suppose if you take V error voltage is equal to V is equal to K pi into pi minus pi by 2. You substitute pi is equal to 0. So K phi into 0 minus pi by 2 means you will get minus K phi into pi by 2. Or if you substitute pi, so K phi into pi minus pi by 2 is nothing but so you will get plus pi by 2. So finally you will get VE max is equal to plus or minus K pi into pi by 2. So you will get the maximum error voltage when the phase shift is 0 or pi. So if we make it, if you take the phase shift is 0, phase angle is 0, you will get the minus K phi by K phi into pi by 2. So if you take phase difference is pi, you will get plus K phi by pi by 2. So finally you will get a plus or minus K phi by K phi pi by 2. And similarly VC max is equal to again the error A times gain. Okay, so A into K phi pi by 2. So now the equation 1 becomes, equation 1 is what? So what we wrote here, this is the equation 1. Okay, and here equation 1 becomes F minus F naught plus KV into VC max. Okay, so VC max. So when that PLL locked and F is equal to, here the new frequency is nothing but your Fs, input frequency. So Fs equal to F naught plus or minus KV. So you substitute VC max in this equation. So A KV K pi by 2, you will get it. Okay, so Fs equal to F naught plus or minus, in the place of it you keep it delta FL. So this delta FL is nothing but our lock-in range. So that is delta FL is nothing but lock-in range frequency. So A KV K phi by pi 2. So from the internal structure they designed K phi value is 1.4 by pi, gain is equal to 1 pi. These are the internal design values. Internal design values we have to take it. So K pi and A, and the substitute here delta phi is A is 1.4, KV is as we know that 8 F naught by V. So 8 F naught by V, and again so K phi is 1.4 by 5 into 5. So simplify it, they will get 7.8 F naught by V and approximately equal to 8 F naught V. Okay, so this is the capture range frequency. And similarly come to this is what lock-in range frequency. Lock-in range is equal to 8 F naught by V. And similarly come back to capture range frequency. So capture range frequency, so what we need is the capture range is the amount of the range of frequency that can acquire the lock. The lock-in range means that can acquire, that maintain the lock, and the capture range is that can acquire the lock. So phase difference between signal and VCO is, and so this is what, this is Fs input signal input signal what we call the angle, and this is output signal angle. So phase difference is this one minus this one, and substitute you take it F omega s minus omega naught into t plus delta theta. So delta theta is nothing but theta s minus theta naught. Theta s is the input frequency angle, and this is the input signal angle, this is output signal angle. Okay, and so if you differentiate on both sides, so the rate of change of phi with respect to the time, the rate of change of phi with respect to time is equal to, you will get F omega minus omega naught into t is there now, so you will get a constant, and this will become 0. So that is 0. So this is the rate of change of phase angle with respect to time. So omega s minus omega naught. So now, so next what you are doing is, after getting that phase detector, you are making the signal to pass through the low pass filter. So if it is low pass, we know that it's A mid-band voltage gain is equal to A by, so low pass filter. So we need not to explain in depth of it. Why? Because we know that. So A mid is equal to A by under root 1 plus F by F1 whole square, where F is what? That is the new frequency. So since we are